Hello, welcome back to the SWAM NPTEL course on tectonics and geodynamics. This is lecture number 12. This time we're going to be talking about plate motions on a spherical Earth. So we are just changing tack a little bit at the moment. So up to now, whatever we have done, we've talked about the motion of a point, right, of plates with respect to each other, imagining that the Earth was flat. Now, fortunately for us, right, unfortunately for the complications, but fortunately for us, the Earth is actually not flat. It's a sphere. So what we really need to be concerned about is whether these principles that we've been talking about so far with respect to a flat Earth, can we actually transform and use them, right, with respect to the motion on a sphere? Can we consider this motion? What happens? What differences these make when we consider this motion to be taking place on a sphere? For this, there is a different concept we have to take into account. We have to think of spherical geometry, and not just spherical geometry, we need to think of motion that takes place with respect to the spherical geometry. And one of the most convenient ways of realizing this comes from the application of a famous theorem framed in the 18th century by one of these famous mathematicians. The name goes by Euler, whom I think many of you have heard in many different contexts before in various fields of mathematics. So there is a particular theory of Euler's which is relevant to this discussion we are having, and this is called Euler's fixed point theorem. So this Euler's fixed point theorem is something that is actually applied. This was adapted to be used, right, with respect to motions of plates on the surface of the Earth. Now, to understand this, we need to go stepwise, right? And just the first thing I always prefer to do in any class is to have a quick recap of what we've learned so far. We now know that even when plates are moving on a flat Earth, right, the geometry of plates can actually change. This changes with time. Many of these changes, what's the primary reason why changes take place? It's because convergent plate boundaries may be convergent, may be divergent, may be strike slip, especially when the same plate has both convergent boundaries as well as divergent boundaries. And along the boundary of a single plate, if these proportions vary, and they will vary, and also the relative velocities across these boundaries may vary, because in most cases there will be different plates which actually will be in contact with one single plate. Normally, a single plate is normally not going to be in contact with one single plate. It will be in contact with a number of different plates. And if this happens, what this means is that the velocities would vary, the rate at which a boundary is created along a divergent boundary and the rate at which it is consumed along a convergent boundary. These will differ, and automatically what will happen is that a plate would either grow in size or shrink in size with time. So this can happen, and this accounts for this change that we are going to see. This is the change that happens all the time when we are actually looking at plates moving on the surface of the Earth, and that's why the geometry of plates as they exist today varies very starkly with what existed in the past, and in fact will vary very starkly with what will exist in the future. Now, the next thing that we actually understood is that when we look at the junctions between three plates, these places called triple junctions, these also significantly they influence the changing geometries of plates on the surface of the Earth. So whenever triple junctions, when these actually move in a particular configuration of plates, when they move, the geometries of these plates on the surface of the Earth, this also changes. So the changing geometry of plates on the Earth's surface, whenever we see, what we can see is that on a flat Earth, we could very effectively use the concept of relative velocities, right, and apply them, because we just considered the relative velocity of one plate with respect to the other, right, and then analyzing the whole motions of plates in, using the theories and the equation that are relevant to relative velocities. We actually found that we could analyze them very efficiently, and we saw largely many changes taking place, many of which are predictable, but many of these which are counterintuitive. So they actually seem to predict things that we didn't know of, and one of the primary examples of this is what we saw happened with the San Andreas evolution and creation of the San Andreas fault. So you had a subduction zone boundary which was converted into a strike slip boundary as a consequence of the intersection of one triple junction with the subduction zone. So things change, the geometry of plates changes, and I find this really fascinating. So now, how would all of these processes differ if we now consider what the Earth really is? It's a sphere. So if we consider a spherical Earth, how would this actually differ? Now, there will be differences, and primarily one of the things is that when we analyze, we normally what we do is to project it on 2D. So depending on the type of projection we use, right, there will be a distortion. There will be a distortion in the geometry. Now, what kind of distortions are we talking about? For example, let us consider the famous Mercator projection, which was used to actually prove the theory of plate tectonics. Now, the Mercator projection, if you remember, we have latitudes and longitudes on a spherical Earth. All the longitudes meet at a point, that the points where the longitudes actually meet on the surface of the Earth, these are called the poles of the Earth. These are the geographic poles. Now, in a Mercator projection, what we do is we flatten this thing out, so the longitudes no longer meet at one point, but they remain parallel to each other. So all the longitudes are parallel to each other. Automatically, what this means is that this conversion, this Mercator projection, when we are converting this, what we see on the surface of a sphere into 2D using the Mercator projection, the areas and lengths of the polar domains, these are actually changed. It distorts the areas and lengths of the polar domains in comparison to what we see in the tropics. So, this is an important point. The consequence of what this means is, I will just elaborate that on the next few slides. Now, even in a rigid plate, the next thing we saw, that even on a rigid plate on the surface of the Earth, in a rigid plate on a flat Earth, obviously at any point on within a rigid plate, we know that if we have a rigid plate like this, so at any point within the rigid plate, so you can actually see that the velocity here, the velocity here, the velocity here, no matter where you are or anywhere on the plate boundary, the relative velocities, the velocities would be exactly the same. That is, within the plate, the relative distances between the points would not change with time. So if this is a plate boundary, all along this plate boundary, the relative velocities between this plate and this plate would remain the same. So that would be the same. However, on a spherical Earth, even when the plates are rigid, the linear velocities that we measure, that, would you expect them to remain constant? Because now geometry, spherical geometry comes into play. Finally, then there's another thing. We analyzed all these changes on a flat Earth using the concept of relative velocity. Can we use relative velocity analysis in the case of a spherical Earth? So these are the important questions that we need to answer whenever we're talking about what happens on a spherical Earth. So what is different? So let's just think of the first thing, right? What the Mercator projection actually does. Now, an example, this is the common way in which the map of the world is represented. I've used one of our old diagrams that we were using. So this is to define the plates. The first time we were talking about plates, I think it was early in our course, we talked about this diagram, and you'll keep on seeing this over and over again. Now notice one thing, you see all of these, this is a sort of Mercator projection. Now notice Antarctica. So this is the Antarctic, right? So the Antarctic that's shown here stretches right across the space of the Earth. Now, as you can see, if you look at this area wise, it's an enormous area. Look at the length that we have of the Antarctic. However, when you actually look at a map of the Antarctic, right, shown on the surface of the spherical Earth, the Antarctic is much, much smaller. In other words, what's been done is that whenever you straighten things out, right, on the surface of a sphere, for example, as a Mercator does, so when you straighten out what you see on the surface of a sphere, then what happens is that the area that you see near the poles, this appears to be much larger. So you actually stretch it out. So it's obvious, you see, you can think of, you see 2 points. Let's just take it into a figure right at this corner. Let's say that you have a point here and a point here. Now, so if you look at this distance and this distance, obviously these two distances, this is larger, this is greater than this. However, now, if I forced these two lines to become parallel to each other, effectively, even if I keep this distance constant here, the distance here that you have, right, between these 2 points, these would also be stretched and become equal to, in proportion to this part here. So as a consequence of making these 2 lines parallel, these are actually parallel to each other on the surface of a sphere, but they are not parallel, right? In fact, by actual definition of parallel lines, they're probably not parallel, because when you actually think of it in terms of the definition of parallel lines, these are points which meet at infinity. Lines of longitudes, in fact, don't meet at infinity, they meet at the poles. So when you actually make them parallel lines on a 2D Earth, then obviously you're going to stretch out this distance much larger. So the area or lines along the poles, right, if you look at these parts which are polar regions, these would actually be stretched out. That introduces a distortion, and this is a fundamental distortion that comes in, particularly in the case of a Mercator projection. But in fact, you will have these different, some kinds of distortions influenced, right, by the type of projection in different types of schemes, projection schemes that we use to convert things from a 3D sphere onto a 2D flat piece of paper or a 2D plane. So how do we then begin to analyze rigid body motion on a spherical Earth? And this is where we come to the concept that is central to what we're going to discuss today. This is Euler's fixed point theorem. Now, how was this theorem originally stated? It was stated as long back. If you look at the bottom, Euler proposed this theory sometime in 1776. It's in the 18th century. And the way he stated was, the most general displacement of a rigid body with a fixed point is equivalent to a rotation about an axis through that fixed point. This was the original statement of Euler's fixed point theorem. So among the many theorems that Euler actually proposed, this is the one that is going to be used by us to analyze plate motions on a spherical Earth. And once again, what he was talking about was a general displacement. If you have a rigid body, right, and it's moving with respect to a fixed point, right, whatever motion it takes place doesn't have to be on the surface of a sphere. The most general way that you can describe that motion is that it's a rotation about an axis with respect to the fixed, that is passing through that fixed point. So it's actually can be considered to be an axis that's passing through that fixed point. So this was the statement of Euler's original statement of the fixed point theorem. Now, if you adapt it, as Mary Fowler did this in her book in 1990, if you restate this, right, and in the form that we can use it with respect to plates, every displacement of one position to another, right, on the surface of the Earth, it can be regarded as a rotation about a suitably chosen axis passing through the center of the Earth. Now, this is a restatement of Euler's fixed point theorem. So Euler's fixed point theorem is something that is actually vital for us. I mean, it's something that is important for us to understand. We restate this in the context of the Earth and while analyzing plate motions. And how do we do it? We actually say, we restate this by saying that any motion that takes place on the surface of the Earth, we can consider it to be a rotation about an axis. We choose this axis. This choice of the axis is up to us, right? A suitably chosen axis passing through the center of the Earth. Now, considering this now, let's just move forward and see what this actually means. Now, what is the Euler pole? Now, this is with respect to the normal poles that we have. So, let's say this is the geographic north, this is the geographic south. So, the Earth actually rotates about this axis, which is the axis of rotation of the Earth. It passes through the center of the Earth. Now, what Euler's theorem actually states is that any motion of any point around the surface of the sphere, on the surface of a sphere, you can actually consider this to be a rotation about an imaginary axis. Now, that imaginary axis, any rotation, that imaginary axis in this diagram, it's this one here, and you can consider it to come out of the other side of the Earth on this side here. So, this imaginary axis that we have, this point, right, it's referred to as the Euler axis of rotation. Okay, it's called the Euler axis of rotation. And the points, now this Euler axis of rotation actually passes through the center of the Earth. And as it passes through the center of the Earth, right, it then passes right through the Earth and it actually penetrates. It's passing through the surface of the Earth at 2 points. Now, these 2 points, the points at which it penetrates or pierces the surface of the Earth, that's the word I'm looking for, pierces the surface of the Earth, these are called the Euler poles of rotation. Now, whenever any point now moves, if you consider it as a rotation, then about this axis, any point will actually tend to move along all of these circles, these dotted circles that are shown here. These dotted circles, these can be regarded as latitudes, right, with respect to this Euler pole. They're not the actual latitudes of the Earth. So the latitudes of the Earth are also small circles, with the only great circle being the one that passes through which is the equator. The latitudes of the Earth, right, these are all small circles, right. So any point that moves on the surface of the Earth with respect to this particular axis, you can regard it as a motion along one of these latitudes. So there may be a motion along here. So all of these would actually pass along small circles. The only great circle it would pass along would be the one that's actually passing through the center of the Earth. Now, all of these, right, this is the form in which motion would take place on the surface of a sphere, right, as small circles, right. All these small circles, these latitudes, note that these are parallel to each other. On the other hand, if you look at the longitudes actually intersect. The longitudes that we have, these actually intersect at the Euler poles of rotation. So with the longitudes, the great circles with respect to that are drawn with respect to this Euler pole of Euler axis of rotation, they actually intersect the surface on the surface of the Earth at the Euler poles. So this is a geometry that is intrinsic to how we begin to analyze. Now, the location of the Euler pole, right, how do we specify the orientation of the axis? It has to be with respect to the orientation of this Euler axis. Now, this the pole of this Euler axis. So this point on the surface of a spherical Earth, to describe the position of a point on the surface of the Earth, there are two things that we use automatically. One thing is called the latitude. The other thing is called the longitude. So the positions of the geographic north and south poles are known to us. So the latitude, right, is the angular distance. It is the angular distance measured from the center of the Earth. So from the center of the Earth, whatever is the angular distance, right, that is subtended by a point on the surface, right, with respect to the center of the Earth, right, that is called the latitude. That is why any point on the equator, right, would have a latitude of 0, right. So any point on the equator would have a latitude of 0. The poles themselves have a latitude of 90 degrees. The longitudes, on the other hand, these are all great circles, right. They pass through the geographic north and south poles. So the position of any point on the surface of the Earth would be given by the intersection of the latitude and the longitude. Now, conventionally, we will use the word lambda here to depict the latitude, right, and we will use phi to depict the longitude. So it's actually just introduced a distortion simply because of the way I'm sitting. So now, okay, so this is phi. So the longitude here, the latitude and the longitude would actually differ, right? They would actually specify the position of any point on the surface of the Earth. So knowing this now, the positions of the Euler poles of rotation can also be specified by mentioning the latitude and the longitude at which they appear. Mind you, these are imaginary points on the surface of the Earth. Now, how do we specify, right, the magnitude? Now, the amount of the rotation, how much it is rotating by, right, that is actually specified, right, by something like omega. Now, this omega term is used particularly when we use it in case of instantaneous rotations, right, something that we call the angular velocity. Otherwise, we can use any term, right. The larger omega term is for large finite rotations, we use omega. So this would actually represent the finite rotations. So this is the magnitude. So the axis of the rotation, the length that we take on the axis of rotation, the magnitude of the actual rotation, it's actually depicted by this axis, by the length of the axis. So omega actually depicts the length of the axis. The position of the Euler poles, they are depicted by lambda and phi. So in other words, we can actually define the position, right, as lambda, phi and omega, which is omega is the actual magnitude. So this would actually specify, right, the amount of rotation associated with any particular axis. However, we must keep certain things in mind here. There is a sign convention that we must follow. Whenever there is a rotation by a magnitude omega, it can be either clockwise, so it can rotate this way, but it can also rotate that way. Now, we have to adopt some kind of convention, right, for this. And the convention that we use is, whenever there is a motion, that when we are looking down the axis from, say, outside the Earth, outside the sphere, when we are looking down this way, so my eye is somewhere here, let us say. So I'm looking down here. So when I'm looking down here, if I see that the motion is anti-clockwise, right, when viewed from outside the Earth, right, the motion, the sense of rotation is anti-clockwise when viewed from outside the Earth, we call that positive. Obviously, it means that if it is clockwise when viewed from outside the Earth, that is negative. So this is the standard sign convention that we will be following, the positive and negative notations when we are looking from outside the Earth. Obviously, it means that if you were looking from the center of the Earth outwards this way or outwards this way, so a clockwise motion when viewed from the center of the Earth would actually be positive. An anti-clockwise motion when viewed from the center of the Earth would be negative. So this way we actually talk about, right, a positive and a negative sense of rotation, which means then obviously it would have opposite senses depending on which ways you look at it. So when you're looking at it this way from here, so let us say when you're looking at it from the center of the Earth here, it's clockwise, right? So when you look at it this way, right, when you're looking at outwards from here, the center of the Earth this way, then it would be anti-clockwise. So one of the poles would be a positive pole, the other pole would be a negative pole. And the sense of the movement, remember that when we are moving now, whenever something moves, so let's say this is one plate B, this is another plate A, then as they are moving, right, the plates would begin to move, then the plate movements would actually be along small circles. They'll be parallel to these small circles here. So this is also along a small circle, this is also along a small circle. So all these movements would be along small circles. So you can see that the velocities, the relative velocity vectors that you have to draw, these will all have to be parallel to small circles with respect to that particular Euler pole of rotation. So any two pairs of plates, right, their motion can be described by the motion of one plate with respect to another. And whenever we're describing the rotation of one plate with respect to another, right, we can use, we know that they must be moving in small circles. Now, rotations, just at this point, there's something very important that's important, and this was something that was identified by one of the early pioneers of plate tectonic theory, Xavier Lapichon. And I think Lapichon's theory came sometime earlier, I think it was in 1973, right? So it's many years ago. So he actually realized that we have to understand that there are two ways in which you can look at rotations. One is a finite rotation, the other is infinitesimal rotation. Now, what do these terms actually mean in the context of the plate movements that we have? The finite rotation is the total amount of movement. So suppose we have two plates on the surface of the Earth. How much is the actual motion of one plate with respect to the other? The total movement. That is called the finite rotation. That is the total amount of movement, which obviously, given the rates of plate motions, these can take place over millions of years. The other one that we have is called an infinitesimal rotation. Now, the infinitesimal rotation refers to motion in small increments of time and by small amounts. Now, when we are talking about finite rotations, the notations we normally use, right, are also different. So the notations we use are omega, right, with respect to finite rotations, and for infinitesimal rotations, we always use something called the angular velocity. So this is the angular velocity. Okay, and the measurement can be either in degrees or in radians. Most of the time we can find it convenient to actually represent rotations in radians. So calculations most often are done in radians. Now, why I'm emphasizing this bit about finite and infinite is because there are 2 points. Plates over a long period of time would obviously undergo finite rotations. There would be displacement of one plate with respect to another, right, over a period of time. That would be over a long period of time, there'd be a significant amount of movement, right, on this on a finite scale. That is what we refer to as omega. And infinitesimal movement, on the other hand, right, is a small scale. So we take this as the movement, the movement that takes place, the angular movement that takes place, right, over a small increment of time. So this is something that actually can be measured in the present day, whereas this you can regard it as the total amount of movement of one plate with respect to another rotation wise. So obviously the finite and the infinite part have to be discriminated between, because there is a very important consequence, right, of what we can apply. All the theories I will show soon can be applied with respect to infinitesimal rotations. We do not apply them to finite rotations. Many of the things that we're talking about do not apply. We cannot use them in the context of finite rotations. So let's just then talk about the theory of finite infinitesimal rotations. Instantaneous is probably something that's better to use. So instantaneous rotations, right, which are, I'm using this interchangeably with infinitesimal rotations. So instantaneous rotations, we regard them to be angular velocities. Now here also there'd be, with respect to the Earth, even a year is an instant in terms of the age of the Earth in 4.6 billion years, then it's actually an instantaneous velocity. So what we are going to use would be the angular velocity, and the angular velocity is omega. Now this omega is depicted in two parts. One is by its magnitude, right, which is this, and then we have a unit vector, let's call this k, right. So this is my unit vector, which is actually the rotation axis, and it's measured by the length of the rotation axis in one particular direction. So omega here is simply the amount of rotation that is taking place per unit time, and this, right, is again the small magnitude of it. When this is multiplied by omega, this is not per unit time, this is what you actually, this is the actual magnitude of the how much rotation has taken place. This actually is the unit vector that defines the direction, the orientation of the axis. So this tells you about which direction I am to apply the rotation to. So the omega vector, the angular velocity vector that we are concerned with, right, would be a multiplication between these two. Now what is important here is that when we are actually applying this with respect to angular velocities here, this is applied to any pair of plates. So what we do is, whenever we have an angular velocity like this, right, we say, just as we did before, angular velocity of plate B with respect to plate A. So we consider one plate. So if you have a circle like this, right, and you have one plate here which is moving with respect to another plate here. So let's call this plate A and this is plate B. So this is their mutual boundary, right? So this is the boundary between plates B and A, and then along this boundary movement is going to take place. That is the relative velocity of B with respect to A. So we consider, when we are considering the movement of B, we have to consider it with respect to A, considering A to be fixed. So this then refers to the relative velocity of B with respect to A. Now all of these are angular motions. Now there is a reason why we represent, when we characterize the motion between these two plates, it's in terms of the angular velocities, and it will be very obvious when we from the next thing that we talk about why we consider we need to represent, we need to characterize the motion between any two plates as angular velocities rather than the actual linear velocities here. And that is because, right, when we talk about rotation poles and rotation vectors on a spherical Earth, right, these have consequences that we can see. So let's actually think of these. When we're thinking of rotation vectors, we think about the relations we have. Now what we can actually, the velocities we actually measure on the surface of the Earth, these are linear velocities, right? So these are linear velocities, and this would be vector v, right? So this itself has a magnitude, has a direction, it's a straight line, so it's a linear velocity here. But we all know, right, the linear velocity, even magnitude wise, v is equal to omega into r. Now here r, let us say this is the, we have to consider this as the radius of the Earth. Okay, so this is the radius of the Earth. When we consider it in terms of vectors, then the v vector, the linear velocity vector, would be the product of the angular velocity vector into the radius of the earth. So v is equal to omega r is what you would actually consider to be the actual motion between this and the surface of the earth. Now let's actually see, let me just go in here now. So let's actually see what this means. Now let's say we have the earth like this, right, and we have velocity here. Let's say we're considering this is, this point B, right, let this be the positive pole, this is the north pole, this is an Euler pole of rotation, and this is a point on the plate boundary, right, between plates A and B, let's say in the last example. So this is the point X represented here. So on this side you can have plate A, and the other side you'll have plate B. So this is a point on the plate boundary. Now what would be the linear velocity? This is what we can actually measure. The linear velocity is what we can actually measure on the surface of the earth. So this would actually be, so if this angle is theta, right, so in that case then the velocity that we have, right, would be equal to v is equal to omega r sine of theta, right. That's the obvious trigonometrical solution we have, right, and we consider this to be my positive pole. So this is the way it is. So v is equal to omega r. This would actually give you the magnitude, right, and the direction would actually be depending upon the direction of the angular velocity vector, right, whatever is the axis of rotation. So when we talk about the direction of the angular velocity vector, this really specifies what is the orientation of the axis of rotation here. So v is equal to omega r sine theta is what we get. Now what does this mean? That means that if we consider just as as an example, let's consider that all of this is a plate boundary, right. If it is, then you can see that although the angular velocity omega would be the same for all points on this boundary, right, the radius of the earth r is obviously same for all points on this boundary, but you can see that the angle theta that it subtends at the center of the earth, right, that would actually be different for different points on this boundary, which means that the linear velocity that is measured on a point on the boundary here, and the linear velocity that is measured on the point of the boundary here, and the linear velocity that is measured on the point of the boundary here, these would be different. So the closer you are to closer the point on the plate boundary is to the Euler pole of rotation, the smaller is the magnitude of the linear velocity. The further you are, right, with a maximum at 90 degrees, right, so when it becomes sine 90, it would just become v is equal to omega r. That would be the condition at which you would get the maximum velocity, linear velocity along a specific plate boundary. So you can see now that linear velocity is one of the questions that we had to answer at the start of this class when we are thinking of movement on a sphere, is whether all points on a plate boundary, even for a rigid plate, would they have the same velocity? Well, linear velocity cannot be different. The angular velocity would be the same, but the linear velocity, right, is most likely different. There would only be one case for one type of boundary in which the linear velocity would be the same at all points along a plate boundary. And I think if you think of it, you can actually begin to guess what kind of boundary that has to be. Now, before we go any further then, for any pair of plates, as I've told you that for any pair of plates, we need to describe their motion with respect to each other in terms of an Euler axis of rotation, right, and a magnitude of the rotation, right. So that is something that has to be there. So this position of the Euler axis of rotation, it is characterized, the poles of the Euler axis of rotation, called the Euler poles of rotation. The Euler poles are each characterized by their latitudes and their longitudes. So conventionally we will use lambda and phi to depict the position of the Euler poles of rotation, and the magnitude of the rotations would be depicted by omega. So if we are talking about A with respect to B, so the angular velocity of B with respect to A, the magnitude of this angle, right, this is per unit time, right, and these, all of these together would actually specify, right, the position, the position of or the relative motion between two plates on the spherical earth. But how do we retrieve this? How do we find this out? Now, one of the things that we can do is to use the strike of active transform faults. How do we locate, say, the position of the Euler poles between any two plates on the surface of the earth? How do we locate the position of the Euler poles? Well, if they share a plate boundary and the plate boundary, let us say, between them is a transform fault, then actually things can be made quite easy. For example, if this is a plate boundary, right? So this is a plate boundary. Let's say that this is displaced by a transform fault like this, and then there's another transform fault like this. We know that a transform fault, right, is essentially strike slip. Now, with respect to the Euler pole of rotation on a spherical earth, since we know that the velocity along a transform fault has to be parallel, right, velocity along, sorry, in this one, yeah, the velocity along a transform fault has to be parallel to the fault itself, then automatically it means that a transform fault must be parallel to the velocity vector. And if it is parallel to the velocity vector on a spherical earth, transform faults must be arcs of small circles. They must be arcs of small circles with respect to the Euler pole, Now, this is a very, very important point. The transform faults, they must be axes of small circles with respect to the Euler poles of rotation. This is absolutely vital. Now, it means then that if we have a long enough transform fault, then you can actually draw, we know that longitudes with respect to the transform fault, right? If we think of the longitudes with respect to transform fault, they will actually be perpendicular to the trend of the transform fault. So, there will be great circles and there will be sort of longitudes. Now, we know that these longitudes then will meet on the surface of the earth, and the point where the longitudes meet, that will be the Euler axis, the Euler pole of rotation. Because let's think of with respect to the latitudes and longitudes of the earth. Just imagine, right, that the earth itself, right, there were two plates, there are two plates, and the plate boundary is any one of the lines of latitude. So, let's say we have a plate A and a plate B. Let's say this is the North Pole, this is the North Pole, and this is South Pole. In this case, the geographic North and the geographic South are also the Euler pole of rotation between plates A and B. Now, we know, let us say the plates A and B have this kind of transform relationship. Then, as plate A moves with respect to B, right, plate A will move like this. Then we know that to find out, suppose I did not know the position of the Euler poles, I can simply draw a great circle on the surface of the earth, perpendicular to the transform fault here, right, another one to the transform fault here, and where they intersect would give me the location of my Euler poles. So, the strikes of active transform faults, these are the easiest way to find out the location, right, of an Euler pole of rotation. However, we can also do this by monitoring the movement velocities along MORs. Now, for example, we know that the velocity of movement, right, it varies as phi is equal to omega r sine of theta. So, we know that the magnitude of the velocity varies as theta. So, as from this itself, we know that along, say, a mid-oceanic ridge, there is a mid-oceanic ridge, let us say, separating two plates. Then along that mid-oceanic ridge, the linear velocity will vary according to this formula. So, we can actually use this change of theta and find out the direction in which theta is decreasing, and from that we can actually find out what would be the location at which this theta would be equal to 0. So, obviously, the plate boundary may not actually pass through the Euler poles. In most cases, it doesn't. So, even when the plate boundary does not pass through the Euler pole, which is in most of the cases, that is what happens. Nevertheless, we can actually use this to actually give us an idea of where exactly the Euler pole of rotation is located. So, this means that we have all the equations that we need, all the notations that we need, and all the conventions that we need, right, with us now. We've understood exactly what we need to be able to analyze the motion of plates on a spherical earth. So, to do this determination of these rotation poles and rotation vectors, as I told you, so we can use this, suppose this is the part, with respect to this you draw the small circles, right, or find out transform segments of plate boundaries. Along them you draw the lines which are perpendicular to the transform faults. They will meet in the poles here, right, and then we can also use the same thing, right. From this we know where the poles are. With respect to geographic north and south poles, we have to specify the positions of the latitudes and longitudes, right? That will give us the Euler poles of rotation. Alternatively, we can use we can use V is equal to omega r sine theta, and using this we can actually try to find out V is equal to omega r sine theta. We can actually use this to find out, right, how the linear velocity actually varies along the surface of the earth. Okay, so given this, now we have all the information we need, right, to be able to proceed to the next step. So before we proceed to the next step, which will be in the next class, let's just summarize what we've gathered together. The relative lengths and areas, right, that we have near the poles and tropics on a spherical earth, right, these are distorted when you project the surface of a sphere into 2D. Now the motions on a spherical earth, you can analyze them using Euler's fixed point theorem, and the relative motion between any two plates on the earth's surface, these can be described using an Euler axis of rotation and the two Euler poles. So what we do then is use these things, identify the locations, and for each pair of plates on the surface of the earth, we define this. We identify the position of the Euler poles and the magnitude of their angular velocities at present, and the instantaneous motions of plates. This is what we analyzed using angular velocities. We can do this. This was another question that we set off to answer. Can we apply the principles of relative velocity to analyzing this? With respect to angular velocities, we can. I will show you in a later class why we cannot do this using finite rotations. So understanding this, right, would be critical to knowing exactly how to analyze the movement between plates. So just keep on following Fowler, moves and twists. And there was an old book which I can't get hold of now, a brilliantly written book by Cox and Hart, which is called, I think it's Plate Tectonics, How It Works. It's out of print and I couldn't find it anywhere, but it's a very readable book which I looked up when I was a student and I found it very useful. Well, more on the spherical earth in our next lecture and motions on a spherical earth. Thank you.